Picture a fragile needle flung toward a spinning vinyl disc, expected to miss, to skitter off into silence. Yet against all odds, it strikes the groove, follows the spiral with flawless grace for a single turn, and vanishes once more into the dark. That near-impossible image is no metaphorical exaggeration. It is the trajectory of 3I Atlas, an interstellar traveler that has threaded the solar system as though obeying choreography written in reverse. With a path tilted retrograde to the planets, it slips past the giants without stumbling into their gravity wells, holding to a vantage point that seems designed for observation rather than accident. In a cosmos where orbits tug and perturbations compound into chaos, its motion is astonishingly exact, almost purposeful, as though the universe itself had conspired to guide this wayfarer. What are we to make of such precision? Is it merely the faint statistical echo of inevitability, the one success amid countless unseen failures? Or are we watching something closer to artistry, celestial mechanics, arranging a performance too perfect to dismiss? Part 1. Was 3I Atlas trajectory chosen? On the 1st of July, 2025, a new name was added to the short and mysterious lineage of interstellar wanderers. First came 1I, Oumuamua, in 2017, a cigar-shaped enigma that defied expectations with its unexplained acceleration. Then 2I Borisov in 2019, a more traditional comet, reassuring in its dusty tail yet still foreign. We thought we had glimpsed the pattern. We thought we understood what visitors from between the stars might look like. We were wrong, for on that July evening, telescopes in Chile recorded something extraordinary, an object hurtling toward our sun at nearly 57,000 kilometers per second, swift enough to circle Earth in under 12 minutes. The mathematics were clear. This thing was no captive of the sun's gravity. It had arrived from elsewhere, and after a fleeting encounter, it would vanish back into the dark ocean of the galaxy. At first glance, it seemed like another chapter in the same unfolding story of cosmic drifters. Yet 3I Atlas, as the object was soon named, carried with it an unsettling grace. This was no chaotic stone tumbling across our sky. It was riding the solar system's invisible highway with eerie precision. Imagine a motorcyclist racing the wrong way down a crowded freeway, yet never straying from the center of the lane. At an inclination of about 175 degrees, 3I Atlas traced a nearly perfect retrograde path, missing exact alignment with the planetary plane by a mere 5 degrees. Out of the infinite vault of space, where trajectories can fall from any conceivable angle, here was one that seemed almost too deliberate. The longer astronomers watched, the stranger the story became. Its projected route read less like a random plunge and more like a carefully drafted itinerary, a brush past Mars, just 1/5 of an astronomical unit, 19 million miles close enough to whisper a greeting, yet far enough to dodge any gravitational entanglement, a skim by Venus at 6/10 of an AU, and the 29th of October perihelion, rounding the Sun before passing Earth again, but at a safe 1.8 AU, some 270 million kilometers away. And finally, a distant rendezvous with Jupiter in March 2026. Each encounter placed it in a vantage point to observe, never so near as to risk capture or disruption. To some, it resembled reconnaissance, a surveyor's arc through the heart of our celestial neighborhood. What made matters more curious was timing. As it reached its closest pass by the Sun, the object would slip into solar conjunction, hidden behind the star's blinding glare, invisible to Earth's telescopes. For a stretch of weeks, just when scrutiny would have been sharpest, it would vanish from view. An accident of orbital mechanics? Or a suspicious coincidence for something that seemed to carry no agenda? In contrast to the maddening silence of Oumuamua, 3I Atlas looked, at least on the surface, like a comet. Hubble's images revealed a glowing coma of vaporized ice and dust, the hallmark of frozen bodies thawing in the solar wind. A faint tail unfurled behind it, textbook in its appearance. Yet even here, anomalies lurked. The coma's brightness leaned oddly forward, concentrated ahead of its motion, while the tail expected to blaze remained stubbornly weak. Explanations proliferated. Some invoked forward scattering effects, peculiar ways in which light reflects off strange dust particles. Others whispered of something more exotic, a crafted disguise, an artificial probe dressed in comet's clothing. Velocity too told a tale. Its 58 kilometers per second pace matched the average drift of stars in our neighborhood of the galaxy. It was not the furious sprint one might expect of a deliberately launched interstellar emissary, nor the sluggish crawl of something barely moving relative to the Sunday. Instead, it was almost suspiciously ordinary, neither too fast nor too slow, the Goldilocks of cosmic speeds. A traveler blending seamlessly into the background noise of galactic motion. Early size estimates only deepened the intrigue. At first, rumors suggested a giant up to 20 kilometers across, a mountain adrift in the void, a vessel large enough to shelter entire cities if hollowed within. But sharper Hubble observations cut that fantasy down. The nucleus appeared modest, perhaps a few kilometers across, perhaps even less than one. Not a mothership, but still a formidable stone, wrapped in an aura of ambiguity. Its discovery came at a moment in history when humanity's eyes are wider and sharper than ever. Projects like ATLAS, the Asteroid Terrestrial Impact Last Alert System, scan the heavens nightly for dangers and surprises alike, hunting the sudden spark of newcomers, the Vera C. Rubin Observatory, soon to awaken, promises to find dozens more such interstellar trespassers in the decade ahead. Perhaps we are merely seeing what has always been there, finally revealed by our vigilance. Or perhaps something else is at play, something sending more wanderers into our path. Scientists, chastened by Oumuamua's confounding legacy, tread carefully. The consensus leans conservative. 3. Atlas is a comet, nothing more, its quirks explained by dust dynamics, by angles of light, by the merciless mathematics of orbital mechanics. Yet there are dissenters. A smaller chorus insists we keep our minds open, that we entertain the possibility of the extraordinary. If a civilization wished to examine us, would it not hide its tools in plain sight, shaping them to mimic the flotsam we already expect from the gulfs between stars? Why announce itself with shining alloys and radio beacons when a lump of disguised ice would slip past unnoticed? Such thoughts linger, feeding the imagination like a cosmic Rorschach blot. Do we see intention because it is truly there, or because the human mind cannot resist weaving story from coincidence? As 3I Atlas sweeps behind the sun in late October, its retreat will look to some like a reconnaissance maneuver, to others like the inevitable geometry of celestial mechanics. The truth, as always, may rest beyond our reach. Authorities assure us there is no danger. NASA and the European Space Agency have emphasized that Earth is safe. The object will never come closer than 4 times the distance to the Moon, a wide berth by cosmic standards. Yet the unease does not lie in risk of collision. The unease lies in meaning. What does it mean to be observed, or to suspect we are? What does it mean to stand beneath the sky and wonder if an alien gaze lingers unseen? The coming months will sharpen the picture. Spectroscopy may unveil the chemistry of its gases, telling us whether this is truly cometary ice or something stranger. Thermal measurements might betray heat signatures no natural stone could produce. Radio antennas sweep the skies, listening for even the faintest whisper of transmission. For now, 3I Atlas is ours to study, visible through September before the sun's brilliance steals it from view. And then, in December, it will re-emerge from conjunction, perhaps transformed by its trial by fire. Comets often change after perihelion brightening, fragmenting, shedding secrets. What will this one reveal when it returns to our sight? We may find nothing more than ice and dust, and the comfort of the ordinary, or we may glimpse something that unsettles our assumptions. Either way, the question hangs in the air, unresolved. Was 3I Atlas's path chosen, or did we merely choose to notice it? In a universe where intent and accident wear the same mask, that distinction may prove more consequential than we dare admit. Part 2: Discovery, Timeline, and Global Observing Campaign. Sometimes the greatest revelations arrive disguised as routine. On the evening of the 1st of July, 2025, two robotic telescopes at the Atlas facility in Rio Hurtado, Chile, were carrying out their nightly ritual. Their mission is not glamorous but indispensable: sweep the sky for anything that moves, anything that might one day collide with our fragile world. Among the thousands of faint specks they logged that night, one was quietly extraordinary. Designated 11PAL3Z by the computers, it was unremarkable to the eye, just another dim point sliding against the backdrop of stars. But its motion was wrong. It crept at the wrong angle, at the wrong speed, tracing an orbit that betrayed no kinship with our Sunday. Within 24 hours, the Minor Planet Center in Cambridge, Massachusetts Humanities Official Ledger for Celestial Small Bodies, had confirmed the suspicion. This was not an asteroid, nor a comet native to our system. Its eccentricity, a numerical measure of orbital shape, was calculated at 6.1. Anything above 1 is unbound, destined never to return. By definition, this object was a wanderer from beyond. On the 2nd of July, the announcement went public. Humanity had met its third confirmed interstellar visitor. Names and designations rolled out with bureaucratic calm: 3I Atlas in the interstellar catalogue, C divided by 2025 N, 1 for its cometary character. Yet the chronology was less straightforward than the press release implied. Archival searches soon unearthed ghostly images from weeks earlier. Both Atlas and the Zwicky Transient Facility had captured its light as far back as the 14th of June, perhaps even sooner. Rediscovery is a prized tradition in astronomy. Each recovered trace stretches the observational arc, sharpening orbital predictions like a lens brought into focus. And what the refined numbers revealed was staggering. At the moment of discovery, 3I Atlas was already 5 astronomical units from the Sun out near Jupiter's orbit, racing at 61 kilometers per second, or 137,000 miles per hour. That is velocity enough to cross the breadth of the United States in less time than it takes to pour a cup of coffee. When corrected for the Sun's gravitational influence, its true inbound speed settled between 57 and 58 kilometers per second, precisely the pace expected of an interstellar body swept into and then through our system. The global astronomy community responded like a single organism, mobilizing across 6 continents in a surge of coordination unthinkable in earlier eras. Within hours of the Minor Planet Center's bulletin, telescopes pivoted, sensors recalibrated, and cameras hunted for the faint smudge sliding across the sky. Amateur astronomers, with backyard observatories and modest instruments, joined the campaign. The Virtual Telescope project in Italy streamed live feeds to the public, letting millions watch as the visitor crept pixel by pixel across the field of stars. Radio arrays began listening, just in case the silence of the cosmos broke with an artificial signal. Press releases from NASA and ESA followed swiftly, their tone measured. Yes, the object was interstellar. No, it posed no danger. Yes, It represented an unprecedented chance to study raw material from another star system. ESA even invoked its Comet Interceptor mission, a spacecraft in preparation to one day chase a pristine comet from the outer solar system, suggesting it might serve as a prototype for future hunts of interstellar prey. Size estimates became the next battlefield of speculation. With only brightness to go on, astronomers were forced into educated guesswork. Was the nucleus a sprawling giant, 20 kilometers across, or something humbler? The problem was compounded by its activity. Unlike Oumuamua's barren silence, this object glowed with a halo from the start. A coma of gas and dust blurred the edges, its photons scattering sunlight like a luminous fog. The challenge of separating nucleus from shroud is notorious. Albedo, the fraction of light reflected rather than absorbed, was unknown. Outgassing levels, which could inflate brightness, were uncertain. Thus, early guesses swung wildly. Headlines trumpeted the arrival of a potential titan, a mountain of ice and rock cutting through our solar system. But Hubble's piercing gaze soon whittled those fantasies down. The nucleus, once stripped of its exaggerating veil, appeared modest, a few kilometers in diameter, perhaps less than one, still sizable, still extraordinary, but far from apocalyptic. The media frenzy was immediate and global. CNN invoked comparisons to Oumuamua. The Guardian unpacked interstellar dynamics for general readers. Science journalists scrambled to turn eccentricities and hyperbolic arcs into language the public could feel rather than fear. Yet beyond the spectacle, the discovery offered a mirror to our own progress. 8 years earlier, Oumuamua had blindsided us, a phantom we noticed only after it had already swung past and was departing. By contrast, 3I Atlas was caught early, tracked at a distance of billions of kilometers, analyzed with instruments that could lock onto its faint light night after night. Our vigilance had grown sharper, our networks swifter, our models more sophisticated. The Atlas system, whose name the interstellar traveler now bore, deserved its share of recognition. Originally funded as an asteroid defense program, its 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa, formed a global sentry, a sentinel chain of lenses sweeping the sky each night. That such a system, designed for planetary protection, had also become humanity's first detector of interstellar emissaries was both poetic and pragmatic. The sky had delivered something new, and we had been ready to catch it. As July gave way to August, the campaign intensified. Ground-based observatories tracked shifts in color and brightness, noting subtle changes as solar heat coaxed gases into space. Hubble prepared deeper sessions, eager to peer past the glare of the coma toward the heart within. Every spectrum captured, every image stored, added brushstrokes to a portrait still blurry but growing sharper. Questions multiplied. Where in the galaxy had this object been born? What frozen chemistry lingered in its nucleus, fossil evidence of a star system light years away? Was its cometary activity typical or subtly strange? And why, above all, did its trajectory seem to glide so precisely through the architecture of our planetary system, aligned just so, retrograde but measured, as if by unseen design? Amateurs and professionals alike knew the coming months promised revelations. 3I Atlas would brighten as it spiraled closer to the sun, and in its shimmering wake might lie answers. The discovery phase was over. Now came the long, patient process of understanding. The night sky had once again delivered its paradox, a faint dot of light, ordinary in appearance, carrying within it an extraordinary story. And as observatories across the world continued their vigil, one certainty cut through the haze of speculation. Whatever 3I Atlas was, It was about to teach us something new about a universe we had only begun to imagine. Part 3. Context and Significance. From Oumuamua to Borisov. Imagine a world where meteorites fall as rarely as lottery jackpots, so rarely, in fact, that entire generations might live and die without ever hearing of one. For most of human history, that was our relationship with interstellar objects. The skies above us were filled with the familiar: asteroids, comets, meteors, all born of our own sun's gravitational dominion. Never, in any recorded epoch, had we knowingly seen a traveler from another star system cutting across our skies. Then, in October 2017, the silence broke. Its name was Oumuamua, Hawaiian for scout or messenger, and it was aptly named. It arrived carrying credentials that declared in no uncertain terms, "I do not belong here." Its orbit was hyperbolic, meaning it was not bound to the sun and would never return. Its color was reddish, hinting at cosmic weathering under alien starlight. Its shape, inferred from its flickering brightness, seemed stretched and elongated, like nothing in our local inventory of cosmic debris. But it wasn't appearance that made Oumuamua infamous. It was behavior. As it rounded the sun and prepared to depart, astronomers noticed an unsettling fact. It was accelerating. Not much, but enough to measure, and crucially, enough to defy explanation by gravity alone. The extra push amounted to about 17 meters per second over its passage, tiny by human standards, but undeniable. The simplest explanation was outgassing, sublimating ices venting invisible jets, as comets often do. Yet no coma, no tail, no chemical signatures betrayed such activity. It was like watching a car speed up without hearing the growl of an engine. Theories proliferated. Maybe it was made of exotic hydrogen ice, sublimating invisibly. Maybe it was a thin, flat object pushed by the sun's radiation, a natural light sail. Or, as Harvard's Avi Loeb provocatively suggested, perhaps it wasn't natural at all. Maybe it was technology, an artifact dispatched across the stars. The debate still lingers, unresolved, suspended between conventional astrophysics and tantalizing speculation. 2 years later came 2I Borisov, and with it, relief of a kind. This interstellar guest was a comet straight from central casting. It grew a luminous coma, sprouted a bright tail, and broke apart near perihelion, succumbing to the same stresses that torment native comets in our solar system. Spectroscopy revealed water vapor, carbon monoxide, and the familiar cocktail of volatiles. And yet, even Borisov was not without its mysteries. Its chemistry revealed a startling richness in carbon monoxide, higher than what we see in most Oort cloud comets. This suggested an origin in an environment colder than the one where our own icy relics formed. It was textbook in its behavior, but alien in its composition. Now, with 3I Atlas, we face a hybrid creature. Like Borisov, it carries the reassuring features of a comet, the halo of a coma, the whisper of a tale. But like Oumuamua, it unsettles expectations. Its path through the solar system, nearly retrograde and astonishingly precise, stirs questions of intent. Its light distribution seems odd, its brightness concentrated in ways that defy simple models. It sits uneasily between the comfort of the familiar and the disquiet of the unknown. Part of what makes 3I Atlas significant is not what it is, but when it came. Until recently, such discoveries were impossible. Our skies have always been crossed by wanderers from other stars, but we lacked the instruments to notice them. Dark, fast, and small, they slipped by unseen. The revolution came with automated wide-field surveys. Linear, Nebraska OIs, Atlas, Catalina. Designed to safeguard us from hazardous asteroids, these eyes on the sky prove just as capable of catching interstellar wayfarers. And now comes the Vera C. Rubin Observatory. With its 8.4-meter mirror and 3.2 gigapixel camera, Rubin will soon scan the entire sky every few nights. Projections suggest it could detect 6 to 50 interstellar objects per year, depending on their size and brightness. What was once the astronomical equivalent of a lightning strike may soon become a seasonal storm. Rarity is dissolving into routine, and with it, the framework of our expectations must change. This perspective matters when we consider 3I Atlas. The temptation is to treat its peculiarities as extraordinary as evidence of something deliberate, perhaps even artificial. But when your sample size grows, anomalies become inevitable. Some objects will pass at uncanny angles, some will burn strangely bright, some will look as though they were guided by an unseen hand. The task is not to dismiss anomalies, nor to leap toward exotic explanations, but to distinguish between the unusual that is natural and the unusual that is not. Here, public fascination complicates the picture. Interstellar objects ignite the imagination, and the media tends to spotlight their mysteries. A cautious scientific paper speculating about artificial light sails can spiral across social networks long before peer review can temper its claims. This is not necessarily a flaw. Curiosity fuels exploration, but it does risk distorting the pace of scientific discourse, making it harder to separate signal from noise. Regardless of the outcome, every interstellar object is a treasure. Each carries the chemistry of another star's nursery, the isotopes of a different history, the scars of alien environments. They are geological samples delivered across light years, messengers that tell us of places we may never reach. 3I Atlas is especially valuable because of its timing and trajectory. Unlike Oumuamua, which we spotted too late, this object was discovered months before its closest pass. We have time for spectroscopy, for thermal modeling, for precise astrometry, time to probe its gases, to map its dust, to watch how it evolves as it nears the Sunday. It is not just a mystery to puzzle over, but a laboratory we can study in real time. It is also a rehearsal, a test of how we respond. How quickly can the global network of observatories coordinate? How well can scientists communicate uncertainty without losing public trust? How do cultural narratives about extraterrestrial life shape the reception of data that may be ambiguous or incomplete? These are not idle questions, because 3I Atlas will not be the last. In the Rubin era, interstellar objects will arrive by the dozens. Some will behave like ordinary comets. Others will defy categories, pushing the boundaries of what we think nature allows. Each will sharpen our skills in observing, analyzing, and most importantly, interpreting. The rarity lies not in the objects themselves, but in our experience of learning how to study them and in our wisdom to temper wonder with rigor. In that sense, 3I Atlas is not merely the third interstellar visitor we have confirmed. It is our third rehearsal, our third opportunity to refine the delicate art of inquiry under the bright spotlight of public fascination. For as these once rare emissaries become familiar, it may be the lessons we learn about ourselves, about how we look, how we question, how we interpret that prove as valuable as any knowledge we glean about their alien origins. Part 4. The trajectory puzzle, geometry, speed, and flybys. Picture a billiard table stretching across the heavens, its felt not green but the black fabric of space. From beyond the table's edge comes a cue ball, 3I Atlas rolling in with uncanny grace. It glides at precisely the right angle, at precisely the right speed, to skim the surface, brushing past other balls without touching. tracing a path so improbably exact it feels like the work of a master player. Then, just as suddenly, it slides off the far edge, vanishing into the dark. In celestial terms, this is no metaphor. It is orbital mechanics written as art. Astronomers classify 3I Atlas's path as extremely hyperbolic, with an eccentricity of about 6.1. To grasp this, imagine the spectrum of orbits. A perfect circle has eccentricity 0. Earth's nearly circular path is a mild 0.017, and all planets live comfortably below 1. A parabola sits exactly at 1, the dividing line between bound and unbound. But 3I Atlas soars far beyond that. With eccentricity over 6, it is radically unbound, barreling through the solar system too fast ever to be held. It borrows only a whisper of momentum from the sun before slipping back to interstellar space, nearly as quick outward as it was inward. The geometry, however, is what unsettles. The visitor approaches from the direction of Sagittarius, toward the galactic center, a trajectory unremarkable in itself, since galactic dynamics funnel many interstellar wanderers from similar bearings. What matters is the inclination. 3I Atlas slices through the solar system at about 175 degrees relative to the ecliptic plane, the thin sheet where the planets circle the sun. This means it moves retrograde, opposite their flow, yet within just 5 degrees of their shared plane. Out of the infinite directions available in three-dimensional space above, below, sideways it has chosen, or happened upon, the razor-thin sliver that lets it skim almost perfectly along the planetary disk. The odds feel staggering. Imagine flinging a frisbee into a multi-level parking garage and having it skim along the floor, neither colliding with ceiling nor wall. That is the strangeness of this alignment. The puzzle deepens with its planetary encounters. On the 3rd of October 2025, 3I Atlas will sweep past Mars at 0.19 AU, about 19 million miles. On the 3rd of November, it glances by Venus at 0.65 AU. After rounding the Sun at perihelion on the 29th of October, at roughly 1.36 to 1.4 AU, it will continue outward toward Earth, sliding past us on the 19th of December at 1.8 AU. Finally, on the 16th of March 2026, it will graze Jupiter's vicinity at 0.36 AU, or 34 million miles. None of these passes is close enough for a gravitational slingshot. Unlike spacecraft that deliberately steal orbital energy to shift course, 3I Atlas takes nothing. These are not maneuvers, but near misses, close enough to capture our attention, far enough to avoid entanglement. The sequence resembles not the chaos of accident, but the spacing of a tour, an itinerary across the inner system. The speeds involved are equally telling. At discovery, it was racing at 61 kilometers per second relative to the Sunday. By perihelion, gravity will accelerate it to about 68 kilometers per second, yet its most revealing number is its v infinity, its asymptotic velocity relative to the galactic neighborhood, 58 kilometers per second. This is precisely what one would expect for natural interstellar debris drifting through our stellar suburb. Not suspiciously fast, not suspiciously slow, but squarely in the Goldilocks zone, camouflaged against the galactic background. An artificial probe might be expected to come screaming in at unnatural speeds, or lingering suspiciously slow. 3I Atlas does neither. Still, its timing seems almost mischievous. As it swings around the sun, it will pass into solar conjunction, hidden behind the solar glare from Earth's perspective. During its most active and scientifically revealing phase, it will be invisible to us. This is common for objects whose perihelia lie between 1 and 2 astronomical units. Yet commonality does not make it less frustrating. The universe has arranged, or appeared to arrange, for its most intimate solar moment to occur beyond our gaze. The Hubble Space Telescope has already visualized its trajectory, elegant arcs of light tracing a hyperbola through the planetary system. These diagrams are both reassuring and uncanny. They demonstrate the serene mathematics of celestial mechanics, the way gravity molds motion into curves of inevitable precision. Yet they also remind us how that precision can masquerade as intent. The path seems to have been plotted to show us Mars, Venus, Earth, and Jupiter without ever letting gravity hold it hostage. Of course, uncertainties remain. Orbital predictions are not absolutes, but estimates bounded by error bars. The perihelion distance of 1.36 to 1.4 AU reflects our current knowledge, subject to refinement. Likewise, the predicted flyby distances may shift slightly as new data tightens the orbital solution. To see precision in these numbers is to forget their provisional nature. What looks choreographed might instead be our instruments painting with blurry strokes, giving illusion of design where only chance reigns. Astronomers refine their models nightly. Each new astrometric observation narrows the uncertainties, chiseling the orbital path into sharper relief. By the time 3I Atlas reaches perihelion, we will know its route with exquisite detail. But the philosophical question will remain: how often do random interstellar paths resemble choreography? Do we only notice the extraordinary because our instruments have finally grown sharp enough to catch them? Or does the elegance of this trajectory whisper of something more? These questions press against the boundaries of science and story. On one hand, celestial mechanics is clear. Eccentricity above 1 means unbound. Inclination of 175 degrees means retrograde. Velocity of 57 kilometers per second means natural by all statistical measures. On the other hand, the geometry feels too clean, the flybys too well spaced, the invisibility during conjunction too coincidental. Perhaps the truth is simpler. In a universe with trillions of stars and untold debris, some paths will, by chance, appear orchestrated. But perhaps, too, the appearance of orchestration deserves our attention. For in studying such cases, we learn not only about comets and hyperbolas, but about ourselves, our hunger for patterns, our fear of being observed, our longing for meaning in the silent arcs of stone and ice. 3I Atlas threads our system like a dancer crossing a stage, bowing neither to sun nor planet, but offering glimpses of many. The geometry is written, the speed is measured. What remains unresolved is the interpretation whether we are watching chaos dressed in elegance or design disguised as chance. Part 5. Comparing to Oumuamua. If interstellar visitors were unexpected guests knocking at your door, Oumuamua would be the shadowy stranger in a trench coat who leaves no fingerprints, vanishing before you can ask their name. 3I Atlas, by contrast, would be the genial neighbor who smiles warmly and chats about the weather, but then lets slip details about your private life you never shared. Both are unsettling presences, but in utterly different ways. Oumuamua exploded into our awareness in October 2017, humanity's first confirmed visitor from beyond the sun's dominion. It broke every rule we thought we understood about how objects should behave. Its brightness variations suggested a body spectacularly elongated, perhaps 10 times longer than it was wide, tumbling end over end, like a cosmic baton. Nothing in our solar system resembled it. Even stranger was its motion. As Oumuamua rounded the sun and began its outward journey, astronomers discovered it was accelerating just slightly, about 17 meters per second over its entire passage, but enough to demand explanation. For comets, Such accelerations are routine, the product of sublimating ices venting gas jets. But Oumuamua showed none of the telltale signs. No coma, no tail, no chemical emissions. It was accelerating like a comet while presenting the face of an asteroid. Scientists scrambled for explanations. Perhaps it was made of hydrogen ice, sublimating invisibly. Perhaps a dark organic crust concealed volatile interiors. Perhaps jets erupted sideways in patterns that escaped our gaze. But the most radical idea came from Harvard's Avi Loeb, who proposed that Oumuamua might be artificial, a solar sail driven by radiation pressure, thin as a sheet of metal foil and shaped more like a pancake than a cigar. Loeb argued that the artificial hypothesis, far-fetched though it sounded, fit the data better than any conventional model. His suggestion sparked a firestorm of debate, one that still flickers today. Then came 2Y Borisov in August 2019, and with it, a sigh of relief. Here was an interstellar object that behaved exactly as the textbooks promised. Borisov sprouted a coma and a luminous tail as it approached the sun, its spectrum revealing water vapor, carbon monoxide, cyanide, the familiar suite of cometary volatiles. It fragmented near perihelion, breaking apart under thermal stress, in a display indistinguishable from that of comets born in our own Oort cloud. Its chemistry did raise eyebrows. Unusually high carbon monoxide levels hinted at a birthplace colder than the environments that shaped our local comets. But it was recognizable, reassuring. Borisov was the cosmic palate cleanser after Oumuamua's riddles. Now arrives 3I Atlas, and with it, another twist in the story. Like Borisov, it looks and acts like a comet, sporting a coma and faint tail from the moment of discovery. Hubble's instruments confirmed the classic signatures, a halo of dust and gas, a pale streamer pointing away from the sunday. But here too anomalies creep in. The brightest emission seems concentrated sunward, ahead of its motion, while the anti-solar tail remains curiously weak. This forward scattering is not impossible for a natural comet, but it is rare enough to raise questions. What unusual properties of dust or grain dynamics are at play here? Or is the geometry telling us something we do not yet understand? The question of size adds further intrigue. Early reports inflated 3I Atlas into a giant, perhaps 20 kilometers wide, a wandering mountain. But Hubble's finer eye pared that figure down sharply. The nucleus is far smaller, with current estimates suggesting less than 2.8 kilometers in radius, maybe just a few hundred meters. This revision matters. A smaller body producing such a vivid coma must be exceptionally active, shedding dust at rates estimated between 10 and 120 kilograms per second. Even at the high end, that represents only a pinprick of its mass, allowing it to sustain such losses for millennia. Yet the efficiency of this process hints at unusual composition or structure, unlike the average comet of our solar family. Hubble's morphological analyses showed the dust emission originating from the sunlit hemisphere, exactly what physics predicts for sublimation driven by solar heating. And yet the geometry gives it a peculiar look, an appearance some interpreters have whispered could be artificial. The spectroscopic evidence, meanwhile, remains hazy. Early attempts to pin down the gaseous composition yielded ambiguous signals, but this is expected. Even Borisov's chemical story only came into focus as it neared the sun, its activity intensifying under heat. Patience, astronomers remind us, is essential. Lining up the three visitors reveals a spectrum of strangeness. Oumuamua was wholly alien, refusing to resemble anything in our catalogues. Borisov was comfortingly familiar, a comet with only minor chemical quirks. 3. I-Atlas rests uneasily between these poles, plainly cometary, yet behaving just oddly enough to keep us from settling into certainty. Brightness patterns underscore this contrast. Oumuamua's light curve varied dramatically, betraying its elongated, tumbling shape. Borisov brightened smoothly, following the textbook curve of sublimating ice. 3I Atlas mostly fits cometary models, but with subtle deviations that spark debates over dust scattering, nucleus activity, and the nature of its coma. This trilogy of encounters reshapes our expectations. Oumuamua shattered the old assumption that all interstellar debris would resemble local comets or asteroids. Borisov reassured us that standard physics still applies. And 3I Atlas suggests the truth lies in a messy middle ground, objects recognizably natural, yet distinctly foreign, with quirks born of environments unlike our own. The challenges of observation have been as diverse as the objects themselves. Oumuamua was already outbound when we spotted it, visible for only a few fleeting weeks before slipping into darkness. Borisov stayed within reach for nearly a year, giving us a long look at its icy theatrics. 3I Atlas, maybe the most generous of all, discovered months before perihelion and observable through multiple stages of its solar passage. This extended window means astronomers can deploy every tool at their disposal: spectroscopy to trace chemicals, thermal modeling to measure heat flow, astrometry to detect subtle non-gravitational nudges. If 3I Atlas deviates from its predicted path, the wealth of data will allow us to disentangle natural sublimation from stranger possibilities. The public reception also follows a pattern. Oumuamua ignited fevered debate precisely because it resisted classification, dangling the possibility of alien technology. Borisov's story, by contrast, passed with quiet fascination, its familiarity dampening controversy. Now 3I Atlas rekindles uncertainty not with glaring anomalies, but with subtler quirks that leave room for interpretation. To the public imagination, subtlety may be even more unsettling. Taken together, the three visitors remind us that interstellar objects cannot be boxed into simple categories. Each carries a fingerprint of the star system that birthed it, shaped by different temperatures, chemistries, and histories. What seems anomalous may, in time, prove to be simply part of the natural diversity of a population we are only beginning to sample. Yet the nagging questions linger. If these are merely random fragments of planetary systems, why do they surprise us so often? And if they are something more, why cloak themselves so carefully in the garb of the ordinary? 3I Atlas, with its mixture of cometary comfort and unnerving peculiarities, feels almost designed to provoke such thoughts. Its behavior is not dramatically alien like Oumuamua's, yet it is not conventionally familiar like Borisov's. It sits in the grey space between, whispering both reassurance and mystery. Whether by cosmic coincidence or deliberate design, it keeps us guessing. And perhaps that is the deeper lesson of these interstellar emissaries, that in the vast silence of the universe, meaning hides as much in ambiguity as in clarity, and sometimes the most haunting message is not what we know, but what we cannot quite explain. Part 6. Signs of anomalies, what looks off and what doesn't. Every good mystery reaches a point where the trail of evidence branches in two directions at once. You have suspects with motives that make equal sense, alibis that appear watertight, and no clear way to decide which thread is real. That is exactly the position we find ourselves in with 3I Atlas. Its dossier of observations contains enough material to support a tidy, natural explanation, yet also enough to tempt more exotic speculation. The puzzle is not that there are anomalies, but that each one can be interpreted in more than one way. The first anomaly is also the most dramatic: geometry. At an inclination of 175 degrees, 3I Atlas is essentially racing in retrograde, threading backward along the same invisible plane where the planets orbit the Sunday. Its tilt is off by only 5 degrees from perfect alignment with the ecliptic. To the human imagination, wired to associate order with design, this looks almost deliberate. Why would an interstellar wanderer born light years away and ejected by the chaos of alien worlds happen to skim our planetary plane so perfectly? Astronomy offers a colder answer. Detection bias plays a starring role. Our surveys, Atlas, Pan-STARRS, Catalina, Zwicky, all spend most of their time scanning along the ecliptic, where native asteroids and comets are thickest. Objects that cross this plane are simply more likely to be spotted. Add to this a subtle dynamical effect. The Sun's gravity, amplified by the distributed mass of the planets, naturally focuses inbound bodies toward the ecliptic. It is not a deliberate alignment, but a kind of cosmic watershed where trajectories are nudged into flatter angles. What looks like intent could, in fact, be inevitability. Then there is the sequence of planetary flybys, which on paper read like an itinerary. Mars at 0.19 AU on the 3rd of October 2025. Venus at 0.65 AU on the 3rd of November. Earth at 1.8 AU on the 19th of December. Jupiter at 0.36 AU in March 2026. A grand tour in perfect sequence. Yet orbital mechanics insists these are not encounters of substance. The distances are too large for gravitational assists. No momentum is exchanged, no trajectory altered. 3I Atlas is not siphoning energy as spacecraft do. It is barreling through on a hyperbolic course, ignoring the planets except as mile markers on its outbound arc. More disquieting is the matter of solar conjunction. At its perihelion, the 29th of October to 30, 2025, 3I Atlas will sit almost directly behind the Sun from Earth's perspective. Just as heating effects are expected to peak when gas jets and dust emission might reveal its deepest secrets, our view will be blinded. To skeptics, this looks like suspicious timing. The object disappears from scrutiny at the very moment it should be most revealing. To astronomers, it is nothing more than orbital geometry. Objects with perihelia around 1 to 2 astronomical units often suffer this fate. It is not hiding. We are simply looking from the wrong vantage. Brightness morphology introduces another thread of intrigue. Hubble's images show luminosity concentrated toward the Sun, with the classic anti-solar tail subdued. To some eyes, this looks like self-luminosity, as though the object were glowing of its own accord. Such an interpretation would be radical, a comet with an internal energy source, inconsistent with passive ice and rock. Yet the Hubble analysis team points instead to forward scattering, a quirk of dust grains reflecting light preferentially in the direction of travel. Rare, yes. Impossible, no. Size estimates, too, have swung wildly. Initial headlines inflated 3I Atlas into a colossus 20 kilometers wide, a mountain that could swallow cities. Those figures were based on raw brightness, uncorrected for coma contamination or albedo assumptions. As higher resolution imaging stripped away the halo, the nucleus shrank. Models now constrain its radius to less than 2.8 kilometers, possibly just a few hundred meters. Still substantial, but no mothership. Yet the revision raises a new puzzle. A smaller body would have to be disproportionately active to generate such a coma. That hints at unusual volatiles, a porous structure, or thermal processes more vigorous than we typically see in comets of comparable size. Dust production estimates reinforce the paradox. Depending on grain size assumptions, 3I Atlas appears to shed 10 to 120 kilograms per second. Numbers that sound large, but in mass terms, are tiny. A few kilometer nucleus could sustain such venting for millennia. The anomaly lies not in the rate itself, but in the efficiency required of such a small body to produce so dramatic an effect. Chemistry, so far, refuses to resolve the picture. Attempts to detect water vapor, carbon monoxide, carbon dioxide, and cyanide have returned ambiguous signals. The lines may simply be too faint at present distances. Astronomers remind us that Borisov's secrets unfolded only near perihelion, when warming drove volatile release into measurable spectra. 3I Atlas may yet do the same. The absence of signatures now is no evidence of strangeness. It may simply be the silence of distance. Still, certain asymmetries nag at the edges of interpretation. Hubble images show dust emissions slightly offset from the nucleus's center. This could mean localized jets from active patches, which is not unheard of in solar system comets, but less common than more uniform activity. Structured emission patterns matter because they could, in theory, betray artificial energy sources or at least mechanisms beyond simple thermal sublimation. Yet, disentangling real asymmetry from instrumental error or atmospheric interference is fraught. Calibrations must be perfect, or illusions masquerade as anomalies. Rotation state is another missing piece. Most comets display brightness variations tied to their spin, as active regions rotate in and out of sunlight. But 3I Atlas, so far, shows no clear periodicity. That could mean an unusually long rotation period, a near-spherical shape, or simply a geometry that masks rotational signatures. The absence of evidence here is ambiguous. It does not confirm abnormality, but it withholds reassurance. And so the picture accumulates. An object that consistently teases, never quite stepping outside the bounds of natural explanation, but never fully settling into them either. Its alignment looks intentional, yet may be the product of gravitational focusing. Its planetary tour looks choreographed, yet delivers no gravitational transactions. Its solar conjunction looks evasive, yet is an orbital inevitability. Its brightness distribution looks artificial, yet can be explained by dust scattering. Its size revision undermines wild early claims, but introduces fresh questions about activity efficiency. Its asymmetries hint at structure, but may be artifacts. Its silence in spectroscopy frustrates, but may dissolve as it warms. The essential dilemma is this: anomalies exist, but anomalies are not proof. Incomplete data exaggerates patterns. Human perception, honed over eons to detect agency in the rustle of leaves or the eyes in the dark, finds meaning where none is intended. In astronomy, as in detective stories, the danger is to confuse what looks improbable with what is impossible. As 3I Atlas continues toward its October perihelion, every new observation is a potential key. Perhaps its chemistry will light up, revealing the same familiar molecules that grace comets from our Oort cloud. Perhaps its dust jets will resolve into patterns consistent with ordinary sublimation, or perhaps its behavior will deepen the strangeness, straying just far enough from expectations to keep the whisper of intentionality alive. For now, the mystery remains unresolved. The anomalies are genuine. Their interpretation is fluid. 3I Atlas sits precisely in that liminal space where natural processes mimic intention, and intention hides beneath the mask of natural law. It is a reminder that in science, as in stories, ambiguity is often the most unsettling outcome of all. Part 7. Natural Explanations, the Comet Playbook. Sometimes the most persuasive solution is the simplest one. In astronomy, simplicity often means turning to the tried and true physics of ice, dust, and sunlight, the same framework that has explained comets in our solar system for centuries. For all its strangeness, 3I Atlas wears one unmistakably natural badge. It behaves like a comet. It outgasses, it glows, it produces a coma and a faint tail. Whatever else we may speculate about its peculiarities, this is the essential and defining signal of a body driven by sublimation rather than machinery. The physics is beautifully straightforward. As 3I Atlas approaches the Sun, solar radiation warms its surface, and subsurface ices sublimate directly into vapor. This escaping gas drags grains of dust with it, lofting them into the surrounding space. The result is the familiar coma, a fuzzy halo of light surrounding the nucleus, visible across millions of kilometers. Observations from the Hubble Space Telescope confirm this process in action. Images reveal a developed coma with clear sunward dust emission and a faint tail pointing away from the sunday. The sunward plume arises because heating is most intense on the day side of the nucleus. The tail emerges as radiation pressure sweeps lighter particles outward, sculpting the cometary form that has entranced humanity since antiquity. Measured dust production rates support this interpretation. Estimates range between 10 and 120 kilograms per second, depending on grain size assumptions. These numbers are entirely ordinary for active comets. They sound impressive until one recalls the scale of the nucleus itself. Even a modest 2-kilometer radius body would contain on the order of 4 billion kilograms of material. At such reserves, it could sustain its present activity for millennia without perceptible loss. Hubble data constrain the nucleus to less than 2.8 kilometers in radius, with some analyses hinting at a nucleus as small as a few hundred meters. This is not unprecedented. Cometary nuclei in this size range are common products of planetary formation, natural leftovers expelled from young systems by gravitational encounters. The brightness morphology, which some have interpreted as unnatural, also finds grounding in comet physics. 3I Atlas appears brightest in the sunward direction, leading to speculation that it might be self-luminous. But forward scattering explains the effect elegantly. When sunlight passes through dust grains, the scattering efficiency depends on angle. For certain particle sizes, forward scattering, where light approaches from behind the particles relative to the observer, is vastly more efficient than backward scattering. This effect enhances brightness along the sun-facing side of the coma, producing exactly the pattern we observe without invoking artificial illumination. It is a trick of light, not a beacon. The orbital dynamics fit naturally into the same framework. Its hyperbolic trajectory, with eccentricity of 6.1, places it firmly in the unbound category. Its asymptotic speed, 57-58 kilometers per second relative to the Sun, is neither alarmingly fast nor suspiciously slow. This is the Goldilocks range expected of material ejected from other star systems and drifting through the galactic disk. Stars orbit the galactic center at different speeds, and when fragments are flung into interstellar space, their encounters with other stars produce relative velocities in precisely this range. 3I Atlas's motion is not exotic. It is routine in the quiet mathematics of stellar dynamics. Even its striking alignment with the ecliptic admits to natural explanations. Ground-based surveys concentrate near the ecliptic, where most asteroids and comets reside, and where observational geometry is most efficient. The likelihood of spotting an interstellar object is highest in these regions. Moreover, the ecliptic represents a gravitational midplane where the Sun and planets collectively exert focusing effects. Interstellar debris is subtly drawn into this sheet, amplifying the chance of discovery there. What looks like a deliberate threading of the planetary plane may simply be the result of selection bias and gravitational shepherding. The timing of solar conjunction, which renders 3A80LAS unobservable at perihelion, also fits the natural playbook. Any object with a closest approach between 1 and 2 astronomical units inevitably passes behind the Sun from Earth's perspective. This is not strategic evasion, it is the geometry of orbits. Likewise, the string of planetary flybys, Mars at 0.19 AU, Venus at 0.65 AU, Earth at 1.8 AU, Jupiter at 0.36 AU, while evocative of a planned tour, is nothing more than coincidence. These distances are too great for gravitational assists. The planets exert negligible influence. The alignments are the happenstance of a hyperbolic track intersecting a system where nearly all the mass lies in a single plane. Spectroscopic results, though incomplete, remain consistent with this natural framing. Attempts to detect specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have yielded ambiguous results, but ambiguity at this stage is expected. Emission lines are faint at large heliocentric distances. With Borisov, many chemical fingerprints only emerged as it drew closer to the Sun, warmed, and outgassed more vigorously. 3I Atlas is likely to follow suit, revealing its chemistry during perihelion passage when production rates peak. Hubble's morphological details, slight asymmetries in dust distribution, an offset brightness peak, uneven emission likewise match what comet scientists already know. Comets are not smooth spheres. They are rubble piles, patchy, porous, chemically heterogeneous. Outgassing rarely occurs uniformly. Instead, localized jets erupt from fractures or volatile-rich regions, skewing the coma and tail. Rotation further complicates the picture as different surface regions cycle through daylight and shadow, modulating activity in irregular rhythms. Such asymmetries are common. They are not signs of technology, but of nature's messy craftsmanship. Even the absence of a clear rotational signal, which some have found suspicious, can be reconciled with known cometary behavior. A long rotation period, a nearly spherical nucleus, or an unfortunate viewing geometry could easily conceal periodic brightness variations. Many comets resist straightforward rotational analysis until their activity becomes stronger or their geometry more favorable. Taken together, these threads weave a compelling natural explanation. 3I Atlas outgasses like a comet. It glows like a comet. It scatters light like a comet. Its orbit, speed, and geometry match what we expect for interstellar debris wandering through the galaxy. Its anomalies, sunward brightness, near ecliptic trajectory, conjunction timing may look suspicious, but each has a straightforward explanation in physics and geometry. To invoke artificiality is tempting, especially in an era when our instruments are sensitive enough to catch details that appear uncanny. But astronomy has a long history of strangeness giving way to simplicity. Pulsars were once LGM, signals little green men before neutron stars explained their regularity. Quasars were once inexplicable, until accreting black holes supplied the answer. Time and again, nature's playbook proves sufficient. This does not mean we should dismiss anomalies out of hand. Each detail deserves careful study, and the possibility of the extraordinary must remain open. But the comet playbook remains our most elegant, economical, and convincing framework. If history is a guide, 3I Atlas will, in the end, settle comfortably within it, not as an alien artifact, but as a natural emissary from a distant star. Its message is not deliberate but still profound, that the galaxy is littered with fragments of worlds we will never see, and that from time to time, one will drift close enough for us to witness the familiar physics of ice and dust playing out in a body born light years away. In the study of mysteries, there comes a point when the evidence piles high enough that one can argue the case in two opposite directions at once. With 3I Atlas, we stand precisely at that threshold. Each observation seems to fit into a natural cometary framework, yet each carries small discrepancies that tug us toward unease. It is the kind of puzzle that lives not in glaring impossibilities, but in the grey fog of ambiguity. The most straightforward gap is rotational. Without knowing 3I Atlas's rotation period or axis orientation, we cannot predict its appearance with confidence. But this uncertainty is hardly surprising. Asymmetric, time-variable activity is the rule for comets, not the exception. Jets emerge from fractured surfaces. Patchy outgassing produces lopsided comae, and rotational effects often mask or amplify these patterns. In our solar system, no two comets behave alike for long. Why should interstellar visitors be any more cooperative? Statistics offer perhaps the strongest natural explanation for 3I Atlas's apparent oddities. As detection technology improves, the population of known interstellar objects will grow. The Vera C. Rubin Observatory, scheduled to begin scanning the skies soon, could reveal dozens of such objects each decade. By sheer probability, some of them will look strange: unusual alignments, odd brightness patterns, peculiar activity rates. In a large enough sample, improbable coincidences are inevitable. The very act of increasing our dataset guarantees we will encounter objects that look special, even when they are not. This is not to say anomalies are meaningless. It is to caution against inferring intention from improbability alone. Patterns emerge by chance as easily as by design. What we call suspicious may simply be the long tail of natural variation. Still, the nagging details accumulate. Consider spectroscopy. By this stage in Borisov's journey, telescopes had already detected water vapor, carbon monoxide, cyanide, chemical signatures that clinched its status as a comet. For 3I Atlas, efforts to capture such fingerprints have mostly failed. Astronomers have reported only upper limits, constraints on how much of a given molecule could be present without detection, not confirmations of its presence. The paradox is obvious. Hubble images reveal a substantial coma and dust production rates that demand significant sublimation. Yet the gases expected to drive this activity are stubbornly elusive. One possibility is compositional. Perhaps 3I Atlas carries more exotic volatile species with weaker emission lines that are harder to detect. Or perhaps ultra-fine dust grains scatter sunlight so efficiently that the coma appears brighter than the gas production rate truly warrants. Both explanations are consistent with physics, but each stretches our expectations. Brightness asymmetry sharpens the puzzle. Forward scattering is a well-known effect. Dust grains can preferentially scatter sunlight in the direction of travel, creating a sunward glow. But the degree of asymmetry in 3I Atlas exceeds what many models predict, especially at its discovery distance. Computer simulations of dust dynamics generally produce more balanced profiles. Here, the sunward concentration appears stronger and more localized, lingering longer than anticipated. Size estimates, too, have proven slippery. Early headlines inflated the nucleus to 10 or even 20 kilometers across, a mountain among comets. Later refinements shrank it dramatically, less than 2.8 kilometers, perhaps only a few hundred meters. This is no crime of astronomy. Size revisions are normal, as comae are disentangled from nuclei. But the implications matter. A smaller nucleus producing such vigorous activity suggests either unusual richness in volatiles or an unusually efficient outgassing mechanism. Both scenarios are plausible, but both place 3I Atlas in the statistical outlier zone compared to comets we know. The alignment problem lingers as well. Astronomers rightly note that survey biases and gravitational focusing funnel us toward discovering objects near the ecliptic, but quantifying exactly how strong those biases are is messy. Models exist, but their error bars remain wide. It is one thing to say, this alignment could happen naturally. It is another to calculate precisely how likely it is when stacked alongside other coincidences. The planetary near misses, the retrograde trajectory, the solar conjunction. Each has a natural explanation. Together, they create a tapestry that still feels uncomfortably neat. Solar conjunction especially deserves a second look. Yes, objects with perihelia between 1 and 2 AU often pass behind the Sun as seen from Earth, but randomness cuts both ways. A different arrival time could just as easily have given us a perfect view of perihelion. Instead, the timing robs us of our best chance to observe peak activity. For skeptics, this feels like evasion. For dynamicists, it is merely geometry. This is where philosophy of science intrudes. Each anomaly invites an auxiliary hypothesis. Brightness asymmetry, forward scattering by unusual dust. Missing gases, exotic volatiles or ultra-fine dust. Alignment with the ecliptic, survey bias and gravitational focusing. Solar conjunction, orbital mechanics, size discrepancy, overestimated albedo. None of these explanations is implausible. But as their number grows, the natural model begins to feel increasingly ad hoc, a patchwork of after-the-fact accommodations rather than bold predictions. The rotation problem illustrates this perfectly. Most comets show periodic signatures as active regions spin into and out of sunlight. 3. I-Atlas shows none. Why? The list of possibilities is long: a slow rotation, a nearly spherical nucleus, a pole on orientation, or uniform surface properties. Each possibility is reasonable, but without independent evidence, we cannot distinguish between them. Flexibility becomes weakness. If any outcome can be explained, then none can be predicted. This difficulty extends to temporal evolution. Comet activity generally follows a predictable trend: brighter as they near the Sun, dimmer as they recede. But the details depend on composition, porosity, rotation, and structure factors unknown for interstellar comets. Without a baseline population for comparison, we cannot tell whether 3I Atlas's quirks are extraordinary or merely representative of a broader diversity we have yet to map. The specter of confirmation bias hovers over all of this. Oumuamua's anomalies primed us to expect strangeness. Every subsequent interstellar visitor is now viewed through that lens. Researchers may unconsciously highlight discrepancies while overlooking consistencies. Media attention amplifies the effect, favoring provocative narratives over cautious caveats. The temptation to frame 3I Atlas as deliberate or artificial grows stronger with each ambiguous data point, even when conventional explanations suffice. And yet, the anomalies remain, small on their own but cumulative in effect. An object that looks mostly like a comet, acts mostly like a comet, but refuses to align neatly with the cometary playbook. The gaps are not gaping holes, they are hairline fractures, the kind that make a structure creak under stress. Whether those fractures reveal hidden complexity in natural physics or something altogether stranger is the question 3I Atlas continues to pose. Perhaps in the years to come, as more interstellar visitors are catalogued, today's anomalies will fade into statistical noise. Perhaps forward scattering brightness, ambiguous gas detections, and odd alignments will prove routine in the fuller spectrum of cometary diversity. Or perhaps these details are signals we are only beginning to hear, whispers that point to new physics, new chemistry, or even new intelligences. For now, 3I Atlas occupies the space of the unresolved. Each observation adds a piece to the puzzle, but also another wrinkle of ambiguity. Its story reminds us that science advances not only by solving mysteries, but by living with them, resisting premature closure, holding space for doubt, and letting the sky teach us at its own pace. The comet looks natural, the anomalies are real, and between those two truths stretches the narrow, fascinating gulf where interpretation and imagination still roam free. Part 8. The idea of intent. What would chosen mean? Imagine yourself stationed in a tower high above the galaxy, a cosmic air traffic controller watching objects cross three-dimensional space at impossible speeds. Some fly wide arcs, some dive inward, some vanish into darkness. If one of those trajectories were not merely the blind outcome of gravity and chaos, but chosen, what would that mean? What, in practice, would intention look like at interstellar scale? This question sits at the heart of our fascination with 3I Atlas. We do not merely want to know what it is, we want to know whether its path is accidental or designed. At its simplest, a chosen trajectory implies active guidance. In our own experience, spacecraft demonstrate this through burns and thruster firings. A sudden spike of acceleration, a vector shift invisible to the naked eye, but measurable by precision tracking, becomes the signature of intent. Even tiny changes matter. Oumuamua showed us that. Its unexplained acceleration amounted to just 17 meters per second in total, barely more than a brisk jog, yet it was unmistakable once astronomers stitched together months of observations. For 3I Atlas, any similar deviations would be subtle to the point of invisibility. Detecting them requires astrometry precise enough to spot whether an object racing at 60 kilometers per second has nudged itself by a fraction of a meter per second. It is akin to trying to tell, from an airplane photograph, whether a single person crossing a football field has adjusted their stride mid-step. So far, no such deviations have been observed. Within our measurement uncertainties, 3I Atlas glides along a perfect hyperbola. But those uncertainties remain wide enough that small corrections could still hide in the noise. A more sophisticated strategy would leave no mid-course signatures at all. Instead of constant adjustment, a civilization could calculate in advance a trajectory that achieves its goals using only natural gravitational physics. Call it ballistic targeting. Choose your launch conditions with such precision that millions of years later, the object arrives exactly where it needs to be, without a single course correction. Such a feat would be difficult to distinguish from natural motion. To us, it would appear as a hyperbola, the ordinary outcome of interstellar debris. The only clue would be statistical improbability. The chance that a random rock just happened to thread such a path is vanishingly low, and yet here, the object island, that brings us to the question of objectives. What might justify such a prodigious act of cosmic navigation? Reconnaissance is the obvious candidate. An advanced civilization might wish to study habitable planets, radio emissions, or industrial signatures from afar. Passing through the inner solar system would provide glimpses of Earth, Mars, Venus, an entire menagerie of worlds. Yet the geometry of 3I Atlas is hardly optimal. Its closest Earth flyby is at 1.8 AU, nearly 270 million kilometers. Even our most powerful telescopes cannot resolve planetary detail at such a distance. If reconnaissance is the intent, the vantage is curiously remote. Another possibility is deployment. The object could, in theory, shed small instruments during planetary passes. These would linger long after the parent body departed, watching quietly. But such deployments would likely betray themselves. Slight changes in trajectory, small debris trails, anomalous flashes of light. None have been observed. Communication relay is another speculation. Perhaps the object carries data, transmitting it back to a home system or to other probes. Such activity might produce electromagnetic emissions or waste heat, detectable with the right instruments. So far, searches have found none. The timing of solar conjunction sharpens the intrigue. During perihelion, the moment of greatest activity, 3I Atlas will hide behind the sun, beyond our sight. If avoidance were a goal, there could be no better strategy. Alternatively, conjunction might be a window for operations invisible to Earth, course adjustments, data transfers, or coordination with other assets. But here we tread deep into speculation, reverse engineering motives from circumstance. Even when we study human beings, inference of intent is fraught. When we turn that lens on hypothetical minds born under alien suns, the risk of projection is nearly total. One can imagine still subtler strategies. Instead of dispatching a single, sophisticated craft, a civilization could seed thousands of objects, each designed to resemble natural debris. Equipped with minimal sensors, they would blend into the statistical background of interstellar flotsam. No radio beacons, no engines, nothing but disguised presence. In such a strategy, detection would not come from one anomaly, but from patterns across many. Only when dozens or hundreds of natural objects were analyzed together would the camouflage fray. And if such probes exist, our current SETI focus listening for signals would miss them entirely. We would be studying them already, cataloging them as comets. This leaves us with a thorny epistemological question. How much improbability is enough? At what point do cumulative coincidences, retrograde alignment, planetary tour, solar conjunction, brightness anomalies, tip the scale from chance to design? Science works by falsifying hypotheses, by predicting and testing. But intelligence complicates this. An intelligent actor can mimic natural processes specifically to resist detection. In such a case, the closer we come to certainty, the more it recedes. History counsels humility. Pulsars were once LGM signals, little green men before neutron stars revealed themselves. Quasars, gamma-ray bursts, fast radio bursts. All began as mysteries that tempted us toward intelligence, all yielded to physics. Yet history also warns against dismissal. If surveillance is happening, it may not announce itself in obvious ways. We might already be cataloging probes under the guise of comets, failing to recognize the fingerprints of intention. In truth, the debate about 3I Atlas forces us to reflect not just on the object, but on ourselves. We are creatures tuned to see patterns, to assign agency. We find faces in clouds and gods in thunder. To us, coincidence often feels like design, and design can hide in the guise of coincidence. Interpreting interstellar visitors is not simply an exercise in celestial mechanics. It is a mirror held up to the psychology of a species hungry to know whether it is alone. For now, the evidence tilts toward nature. 3I Atlas behaves as a comet should. Its coma, tail, and dust production fit the physics of sublimation. Its trajectory conforms to gravity's relentless law. Its speed matches the background hum of galactic motion. Yet shadows remain. Improbable alignments, gaps in gas detection, subtle asymmetries. Each can be explained by dust, by bias, by geometry. Taken together, they whisper the possibility of something more. What would chosen mean? It would mean that across unthinkable distances, intent had been preserved, precision maintained, and purpose hidden within the mathematics of hyperbolas. It would mean that someone or something had aimed, and that aim had landed squarely in our cosmic neighborhood. Whether or not that is true for 3I Atlas, the possibility itself is enough to haunt us. The comet continues on, its path carved by gravity or perhaps by design. For us, the distinction matters less than the discipline to hold both possibilities in tension, to admit the allure of intent without abandoning the rigor of evidence, to recognize that sometimes the universe delivers us puzzles that cannot be solved cleanly, only lived with. 3A Atlas may be one such puzzle, its trajectory both natural and uncanny, its meaning both simple and profound. Part 9. Cosmic Scales of Chance. How unlikely is this path? Picture, if you will, a casino the size of the cosmos. The dice here have billions of faces. The roulette wheels spin through dimensions our minds can't fully picture, and every trajectory of every wandering fragment of rock or ice is the result of one such throw. In this casino, improbability is not exceptional, it is inevitable, because the universe has had eons to roll the dice. And yet, when we look at 3I Atlas's path through our solar system, our pattern-hungry brains insist on seeing purpose, as though the dice had been loaded. The challenge lies in learning how to separate genuine anomaly from statistical inevitability when the scale itself overwhelms human intuition. Start with the geometry. The ecliptic plane, where our planets orbit, is a paper-thin slice of possibility in an otherwise infinite sphere of approach directions. A random trajectory could in principle come from anywhere, at any inclination. To have 3I Atlas arrive within 5 degrees of that plane feels like threading the eye of a cosmic needle. Naively, it looks vanishingly unlikely, but naive estimates ignore the way we search. Our ground-based surveys are optimized to find objects near the ecliptic where most asteroids live, where telescopes spend the bulk of their time, where atmospheric and geometric conditions are most favorable. We are dozens of times more likely to spot a visitor in this slice than in the high inclination void above and below it. Add to this the gravitational shaping of trajectories. The sun and planets bend paths inward, subtly guiding slower interstellar bodies toward the solar midplane. Simulations show this focusing effect increases the odds of ecliptic alignments far beyond what geometry alone would predict. The result is a skewed deck. We notice the cases that look aligned because our instruments are built to notice them. Now consider the sequence of planetary encounters that so neatly dots 3I Atlas's itinerary. Mars, Venus, Earth, Jupiter, one after the other, in apparent order. To the casual observer, it reads like choreography. But again, definitions matter. What counts as a close encounter? For spacecraft, a flyby at a few thousand kilometers is close. For a comet, close might mean tens of millions of kilometers missed distances so wide that the planet's gravity hardly tugs at all. In that regime, sequences of multi-planet passes are not rare but almost guaranteed. Any retrograde trajectory skimming the ecliptic is bound to sweep past several worlds simply because that is where the worlds are. The sequence is less a deliberate itinerary than the byproduct of geometry. Solar conjunction offers another apparent miracle of timing. At perihelion, the very moment when 3I Atlas should be most active, it passes behind the sun from our perspective. Our instruments will be blinded just when we most want to look. This seems suspicious, even evasive, until you realize that any body with a perihelion of 1 to 2 astronomical units will do the same. Conjunction is not a trick, but a necessity, repeated again and again by the countless asteroids and comets in our own system. It feels like misfortune because we care about this one object. In the statistical ensemble, it is the rule, not the exception. Why then do these coincidences feel so heavy with meaning? The fault lies with our evolutionary inheritance. Our ancestors survived by spotting intention in the rustle of grass or the gaze of a predator. Better to mistake wind for a stalking lion than the reverse. That bias toward agency now misleads us at cosmic scales. We are startled by patterns that may be no more intentional than the shared birthdays in the famous paradox. In a room of 23 people, the odds are already better than even that 2 will share a birthday. The improbability dissolves once you realize the question is not, what are the odds these 2 match, but what are the odds any 2 match? Likewise, with interstellar visitors, we are not calculating the chance of this exact path, but of any path that looks improbable in retrospect. The Rubin Observatory will deepen this lesson. By the end of the decade, it may discover dozens of interstellar objects per year. Inevitably, some will have alignments, brightness patterns, or encounter sequences that look designed. With larger numbers, the improbable becomes routine. The statistical expectation is not that all visitors look mundane, but that some will look remarkable because the more rolls of the dice, the more extreme outcomes appear. Complicating matters further is publication bias. Both scientists and journalists are drawn to the unusual. A comet with a perfectly ordinary hyperbolic orbit is unlikely to generate headlines. One with improbable geometry, ambiguous chemistry, or exotic alignments will. Our perception of rarity is skewed because the sample we read about is not the true population, but the highlighted outliers. Statisticians warn about another trap: multiple testing. If you look for enough anomalies, alignment, conjunction, flyby sequence, brightness asymmetry, you are bound to find some. Each has a small chance of occurring, but taken together, the odds of at least one anomaly appearing somewhere in the dataset rise rapidly. Without correcting for this, we overestimate significance and convince ourselves that design lurks in noise. This is the real cosmic scale of chance. Improbabilities multiplied not by one trajectory, but by billions of opportunities. Over the vast reaches of galactic time, fragments like 3I Atlas have crossed into our solar system countless times. Most went unseen. Of those we catch now, some will carry geometries that look uncanny. The challenge is not in finding such anomalies, but in resisting the temptation to interpret every roll of the dice as evidence of intent. And yet, the tension remains. For while statistics explain why improbability is inevitable, they do not erase our sense of strangeness. The coincidences pile up, the mind rebels. What if chance is not enough? What if, within the great casino of the cosmos, some dice are indeed loaded? That possibility cannot be disproven, only weighed against the growing body of evidence that natural explanations suffice. 3I Atlas sits in this uneasy space. Its orbit looks improbable, but our tools and biases make such improbability expected. Its encounters look choreographed, but geometry guarantees them. Its timing feels suspicious, but perihelion conjunction is routine. Whether we see anomaly or inevitability depends less on the object itself than on how we choose to measure probability at cosmic scales. The comet rolls on, indifferent to our calculations. To us, it is a messenger, reminding us that the universe is both law-bound and chance-driven, both predictable and surprising. Its path is not a verdict, but a mirror, showing us how fragile human intuition becomes when stretched across the scales of stars. When we examine any complex object in detail, whether it is a comet, a star, or a fragment of interstellar debris, we are in effect running a battery of statistical tests. For 3I Atlas, those tests span orbital geometry, brightness profiles, spectroscopic fingerprints, temporal evolution, and more. Each test carries some chance of producing a result that looks significant purely by accident. When dozens or even hundreds of such analyses are performed, the probability that at least one will produce a seemingly anomalous outcome rises dramatically, even if the object itself is entirely ordinary. This is the danger of post hoc reasoning. We tend to define unusual based on what we happen to notice, rather than on criteria we set in advance. Proper statistical discipline would require pre-registering hypotheses, specifying beforehand which characteristics we consider markers of anomaly and what probability thresholds distinguish signal from noise. Without that rigor, random fluctuations can masquerade as meaningful patterns. Velocity offers one of the clearest checks against exaggerated claims of artificiality. 3I Atlas moves at 57-58 kilometers per second relative to the local standard of rest, precisely the speed expected for debris belonging to the thick disk population of our galaxy. Faster motion might hint at artificial propulsion, a deliberate push across interstellar distances. Slower speeds could imply braking maneuvers intended for capture, but this Goldilocks velocity is strikingly mundane, neither too fast nor too slow, exactly what natural galactic debris should exhibit. Physics also imposes limits that any hypothetical targeting system would struggle to evade. Precision navigation on interstellar scales requires energy expenditures that escalate dramatically with accuracy. To engineer a trajectory with milli-arc-second precision enough to orchestrate planetary flybys across light years would demand propulsion capabilities, orders of magnitude beyond human technology. Such maneuvers would likely leave physical signatures, exhaust plumes, thermal emissions, electromagnetic interference. No such evidence has been found. This doesn't prove artificial guidance is impossible. A civilization vastly older than ours might harness principles we cannot imagine. But the absence of any detectable traces strongly suggests that, if intent exists, it operates at levels indistinguishable from natural gravitational choreography. The deeper difficulty lies in our vanishingly small sample size. To date, we have confirmed exactly 3 interstellar visitors: Oumuamua, Borisov, and 3I Atlas. 3 points define no reliable distribution. We cannot yet say what normal looks like for interstellar wanderers, how common their alignments with the ecliptic should be, how typical their brightness asymmetries are, or how varied their volatile compositions might become. What appears unusual in this tiny dataset could, with a dozen or 100 discoveries, prove utterly commonplace. Conversely, what we consider standard cometary behavior might dissolve into one subset of a far broader spectrum. Only with expanded surveys like the Rubin Observatory will we gather the statistical power to separate true anomalies from natural diversity. Until then, every claim about improbability rests on fragile scaffolding, assumptions about detection biases, survey strategies, and population models that remain untested. In this context, labeling 3I Atlas's path as deliberate or coincidental risks overstepping what the evidence allows. For now, all we can say is that it moves along a precise, hyperbolic arc, one that could be read as either the product of blind celestial dice rolls or of unimaginable intent. Perhaps the distinction matters less than our recognition of scale. In a universe vast enough to contain billions of stars and trillions of potential wanderers, even the most improbable patterns will eventually appear. Given time enough, chance alone will craft alignments so uncanny that they whisper of design, whether or not any hand has guided them. Part 10. The Alien Probe Hypothesis. Why it won't go away. There is something magnetic about the suggestion that we are not alone. A gravity of imagination that tugs at even the most skeptical mind. It is one thing to marvel at comets and asteroids, to treat them as frozen fossils of planetary formation. It is another to entertain the possibility that some of them might be messengers, designed with intent. Oumuamua, cracked that door open in 2017, and 3i Atlas has kept it from swinging shut, no matter how many conventional explanations we stack like sandbags against it. The persistence of the alien probe hypothesis is not just tabloid fodder or Hollywood fantasy. It grows out of a real tension inside the scientific community: how to balance the discipline of skepticism with the imaginative openness required to recognize extraordinary discoveries. That tension sharpened with Oumuamua, whose anomalous acceleration and silence in every other wavelength prompted Harvard's Avi Loeb to argue that artificial explanations should remain on the table. His stance sparked a debate that rages to this day, and with 3i Atlas's arrival, the debate only deepens. Loeb and his collaborators do not claim certainty. Their method is to keep multiple hypotheses alive until evidence forces closure. In the case of 3i Atlas, they point to its retrograde, near-ecliptic path, its sequence of planetary encounters, and its unusual brightness, morphology, as features worth scrutiny. Their plea is not, "This is a probe," but "Do not close the case too early." To some astronomers, this is admirable intellectual caution. To others, it is reckless speculation, feeding public misconceptions and conspiracy theories. The Hubble Space Telescope's clear detection of outgassing and dust has given weight to the conservative view. A comet is a comet, many argue, even if its details are untidy. But the fight is not really about this one object. It is about the philosophy of science itself. How conservative should we be when faced with anomalies? How much risk is there in entertaining hypotheses that extend beyond the known? To some, invoking alien probes without extraordinary evidence undermines credibility. To others, ignoring that possibility risks blinding us to discoveries that would change everything. The media compounds the difficulty. Stories with the phrase "alien probe" in the headline travel farther than sober reports about dust jets or sublimation models. Peer-reviewed papers on cometary physics rarely trend on social media, while speculative blog posts about extraterrestrial technology go viral in hours. Journals and researchers, too, are caught in the undertow of incentives. Bold claims attract citations and coverage, while mundane confirmations fade. The result is a distorted picture of scientific consensus, one in which nuance is lost between poles of denial and proclamation. The Galileo project emerged in this climate, an effort to build instrumentation designed not just for astronomy, but for technosignature archaeology. If our telescopes and surveys were built with natural objects in mind, perhaps we are blind to subtle evidence of artificiality. Infrared glows inconsistent with passive heating, geometric edges visible only in high resolution, trajectory nudges smaller than current astrometry can resolve all might slip past our current filters. The Galileo project treats Oumuamua and 3i Atlas not as unique mysteries but as prototypes for a new mode of investigation. That approach overlaps with the concept of astroarchaeology, the idea of searching systematically for artifacts in space. Just as terrestrial archaeologists infer cultures from ruins and fragments, astroarchaeologists might seek unusual orbital clusters, anomalous compositions, or objects whose statistics break the mold. The question shifts from, is 3i Atlas artificial, to what would artificiality look like across a population? A single comet-like visitor may never resolve the debate. 100 visitors, carefully catalogued, might. Population-level patterns would be the true test. Natural interstellar debris should follow distributions rooted in planetary formation physics and galactic kinematics. A wide range of sizes, compositions tied to stellar nurseries, velocities consistent with thick disk dynamics. Artificial objects might reveal different signatures, unexpected uniformity, clustering at sizes or velocities impractical for nature, trajectories optimized for observational coverage of habitable worlds. But such patterns can only emerge once the sample grows, and the Vera Rubin Observatory promises to supply that growth. Within the coming decade, it may detect dozens of interstellar objects annually, giving us the numbers to trade speculation for statistics. In the meantime, case studies like 3I Atlas remain invaluable training grounds. Even if it proves entirely natural, the process of interrogating its data-building models, refining instruments, parsing anomalies prepares us for what comes next. As detection rates rise, we will need to make quick judgments about which visitors merit deeper study, which can be classified as routine, and which deserve to be watched with more open minds. But beneath the scientific debate lie ethical and cultural stakes. If we ever confirm an artificial interstellar object, the consequences for humanity will be profound. How should such knowledge be communicated? The SETI community has protocols for radio signals, but none for material artifacts. Should ambiguous evidence be publicized, risking panic or premature conclusions? Should it be withheld, risking erosion of trust? These are not hypotheticals. They are questions we must be ready to face. Public understanding is central to this challenge. Science communication that dismisses the exotic too harshly risks alienating the public, feeding suspicion that evidence is being buried. Communication that oversells anomalies risks discrediting science when more mundane explanations emerge. The line between openness and sensationalism is razor thin, and walking it requires candor about both what we know and what we do not. Ultimately, the alien probe hypothesis endures because it is not really about Oumuamua or 3I Atlas at all. It is about us. It is about the ancient ache to know whether intelligence flowers elsewhere, about the stories we tell ourselves when confronted with the silence of the sky. Are we a lonely spark in an indifferent void, or are we watched, perhaps even studied, by civilizations whose tools masquerade as comets? The persistence of the idea is not proof of its truth, but a measure of how deeply it resonates. As 3I Atlas sails onward, it carries this resonance with it. Its coma glows, its trajectory arcs, its anomalies hover on the threshold of significance. We may never know for certain whether intent shaped its path, but in struggling with that question, we reveal our own intent: to search, to imagine, to refuse to accept easy answers. The probe hypothesis lingers because it touches that core of human curiosity, the restless conviction that the cosmos holds stories not yet told, and that some of those stories may one day include us. Part 11. A trajectory toward Earth, or just through the inner system? Few things ignite speculation quite like misunderstood orbital geometry. When news outlets first reported that 3I Atlas would approach Earth, headlines conjured images of an interstellar visitor on a direct course for collision. The reality, as always in astronomy, is at once more mundane and more fascinating. Rather than beelining for our planet, 3I Atlas will slip through the solar system's inner regions like a threaded needle skimming past multiple worlds, never coming anywhere close enough to pose a threat and offering a vivid demonstration of celestial mechanics in action. Let's lay out the itinerary in detail. On the 3rd of October, 2025, 3I Atlas will pass Mars at about 0.19 astronomical units, AU, roughly 19 million miles. To human intuition, that sounds close. By planetary standards, it is. Nearly 20 times closer than Mars ever comes to Earth at opposition. Yet it's still about 50 times the Earth-Moon distance. Close enough that Martian orbiters, if aligned properly, could wave at the visitor, but nowhere near an actual near miss. At perihelion, On the 29th of October 30, the comet will dip inward to 1.36, 1.4 AU, just inside Mars's orbital distance. This is the gravitational peak of its visit, the moment of maximum solar heating, when buried ices sublimate most vigorously and outgassing peaks. For natural comets, this is often when activity becomes dramatic, tails lengthen, comae brighten, jets flare. For 3I Atlas, this will be the critical window for understanding whether its behavior follows familiar cometary patterns or veers into the unexpected. The Venus encounter comes next on the 3rd of November at 0.65 AU, 60 million miles. Again, impressive on paper, but in practice far too distant for mutual influence. No spacecraft-style slingshot, no gravitational dance, just a brief passage through the same broad sector of the solar system. The flyby that generates the most headlines is Earth's. On the 19th of December, 2025, at 1.8 AU, 270 million kilometers. To casual readers, approaching Earth sounds ominous. Yet, astronomically speaking, this is an enormous gap, about twice the distance between Earth and Mars at closest approach. NASA and ESA stress repeatedly that the object poses zero danger. Even if orbital models were off by millions of miles, Earth would remain perfectly safe. Still, media fascination persists, in part because the geometry of space is counterintuitive. What counts as close in cosmic terms is still unimaginably far in human ones. Finally, on the 16th of March, 2026, 3I Atlas will pass Jupiter at 0.36 AU, 34 million miles. By raw numbers, this is the closest planetary approach of its entire solar passage. But even here, the scale is deceptive. That's still 80 times the Earth-Moon gap. The object will glide through Jupiter's realm without meaningful deflection, an interstellar tourist who admires the giant from afar before slipping back toward the deep sky. This sequence, dramatic as it looks on diagrams, is not evidence of a planned tour. It is the inevitable consequence of a hyperbolic path slicing across a planetary system where most major bodies orbit near the same plane. Like threading a string through beads scattered on a table, the comet's path intersects multiple orbits simply because those orbits lie in its way. The appearance of intentionality, Mars, Sun, Venus, Earth, Jupiter, in neat succession, is a product of projection, not navigation. Here lies the heart of the misunderstanding. We humans think in terms of journeys, choosing stops, optimizing routes, plotting itineraries. Orbital mechanics doesn't work that way. 3I Atlas's course was fixed the moment it crossed into the Sun's gravitational influence. Every subsequent encounter is geometry, not choice. Planets are not targets but waypoints coincidentally nearby as the comet arcs through space. This matters for evaluating the probe hypothesis. A reconnaissance craft would be expected to approach planets much more closely, especially Earth. At 1.8 AU, 3I Atlas cannot obtain high-resolution views of our world. Even Hubble struggles to resolve major surface features of Mars at 1/100th that distance. From hundreds of millions of kilometers, even an advanced sensor suite would be blind to anything but gross planetary characteristics, hardly efficient surveillance. Nor is the geometry favorable. The comet's retrograde orbit means it will often see planetary night sides during closest passes, limiting observational potential even further. And if concealment were the goal, the solar conjunction at perihelion would seem clever, shielding the comet from scrutiny during peak activity. Yet conjunction is not contrived. It is an unavoidable artifact of orbital mechanics for any perihelion in the 1–2 AU range. Far from cunning camouflage, It is a hindrance for observers, an accident of perspective repeated by countless asteroids and comets. Indeed, the trajectory looks less like reconnaissance and more like inefficiency. Why would a civilization capable of interstellar flight accept such poor geometry for observation? Why not engineer a closer Earth pass or insert into a stable orbit for long-term study? The simplest answer is because there was no intention. 3. I-Atlas is not optimized for reconnaissance because it was never meant for reconnaissance. Astronomers will still squeeze as much science as possible from this visitor. Space-based observatories, less limited by solar glare, will track it before and after conjunction. Hubble and JWST could probe dust and gas properties, while ground-based arrays will refine its trajectory through astrometric campaigns. The post-perihelion window, in December 2025 and beyond, will be especially valuable. Many comets brighten or fragment after close solar passages, revealing volatile reservoirs or structural weaknesses. If 3I Atlas follows that script, it will strengthen the natural comet interpretation. If it does not, if it resists thermal stress unnaturally well, or shows behavior inconsistent with sublimating ice, then debates about its nature will reignite with fresh intensity. For now, the balance of evidence points to gravitational inevitability. The Mars, Venus, Earth, and Jupiter encounters, the inconvenient conjunction, the large safety margins, all align with the physics of a body on a hyperbolic trajectory set long before it ever neared our Sunday. The Earth flyby is only a flyby in name, distant and harmless. The interstellar traveler is not coming to Earth, but merely through the solar system, pausing briefly in our neighborhood before vanishing into the dark again. And yet, the open question lingers. If intent were ever encoded into the object's initial approach, before it even brushed the edge of the sun's domain, that intent would be nearly impossible to disentangle from natural dynamics. Every planetary passage could be coincidence or consequence. Every conjunction could be geometry or design. That ambiguity is what fuels speculation. But the story written in the numbers is clear. 3I Atlas is passing by, not visiting. Would you like me to also draft a visual-style trajectory chart with perihelion and planet flybys labeled, so you can drop it alongside this text? It could help anchor the geometry in readers' minds and counteract the misleading Earth approach headlines. Part 12. Testing Humanity, a Speculative Lens. What if 3I Atlas isn't here to study the sun, the planets, or the icy debris at the edge of our system, but to study us? This is, of course, speculation. Yet speculation serves a purpose: to test ideas, to hold a mirror up to our assumptions. In this frame, 3I Atlas becomes not just an object of study, but an experiment, its real subject being humanity itself. Psychologists often disguise the aims of their experiments. Volunteers think they're testing memory or perception, when in truth the experiment measures conformity, ethical choices, or bias. By analogy, an interstellar visitor could present itself as a natural cometary wanderer, while in fact functioning as a probe to reveal how a young technological species responds to ambiguity and possibility. Already, 3I Atlas has generated a remarkable stress test of human systems. Within hours of its announcement, telescopes across 6 continents coordinated observations through the Minor Planet Center. Professionals joined forces with amateurs. NASA and ESA issued calm, measured statements. Yes, it's interstellar. No, it poses no threat. Yes, it's an opportunity. Meanwhile, media outlets speculated wildly. YouTube channels filled with theories, and social networks oscillated between sober curiosity and conspiratorial frenzy. If you were an observer looking not at the comet but at us, the data would be invaluable. The timeline itself almost feels designed for maximum effect. Discovery came months before perihelion, long enough to plan campaigns, not so long that public interest fades. The object slips behind the sun at the height of its activity, forcing us into a test of patience, predictive skill, and institutional discipline. When it emerges again, our success or failure at forecasting its behavior will be plain to see. The characteristics of the comet feel almost calibrated to create debate without panic, too obviously artificial, and civilization might recoil in fear, too mundane, and we would shrug it off. Instead, 3I Atlas hovers in a liminal zone. Its hyperbolic orbit and cometary activity are natural enough, yet its ecliptic alignment and ambiguous morphology provoke discussion. It forces us to confront our statistical blind spots, our biases toward intentionality, and our hunger for narrative. The planetary encounter sequence is another mirror. Do we see mere coincidence or reconnaissance? Our answer says less about the comet and more about the human tendency to anthropomorphize, to see agency in randomness. This is exactly the kind of cognitive vulnerability that would interest any intelligence gauging our readiness for first contact. The media's role becomes an entire data stream of its own. Thousands of articles, podcasts, posts, and debates erupted in the first days after discovery. The spectrum of response from rigorous breakdowns to outlandish claims maps our cultural ecosystem in real time. How do we handle uncertainty? How do authority, expertise, and speculation compete in the attention economy? To external observers, this torrent of discourse might reveal more about humanity than any telescope image of Venus or Mars. Institutional responses, too, speak volumes. NASA and ESA modeled restraint, tamping down hysteria without dismissing wonder. Academic astronomers leaned heavily toward natural explanations, but most acknowledged uncertainties. Peer review moved at its deliberate pace, offering slow but careful judgment. All of these behaviors would give an external analyst insight into our risk management, our appetite for evidence, our cultural values around science. Even our errors tell a story. Early headlines reported a massive 20-kilometer nucleus. Subsequent Hubble analyses revised that down to a few kilometers at most. This misstep, and our ability to correct it, would reveal to any watchers how quickly we identify flaws, update models, and communicate uncertainty. Do we learn, or do we double down? 3I Atlas makes that visible. Solar conjunction provides perhaps the most refined element of this hypothetical test. By disappearing behind the sun during peak activity, the object creates a natural experiment in delay. Can we sustain observation programs through the dark? Do we accurately model what we cannot yet see? Can we resist filling gaps with speculation? Tracking an object through conjunction requires not only patience, but also coordination of space-based assets and data sharing across borders. It becomes a test of both our technology and our global cooperation. The speculation itself is data. The fact that we openly debate whether 3I Atlas might be artificial demonstrates that we recognize the possibility of intelligence beyond Earth. Our narratives betray both our fears that aliens might lurk unseen and our hopes that we are not alone. For any external evaluator, this reveals the contours of our cosmic psychology, a species aware of the stars, yet uncertain of its place among them. Perhaps the most encouraging signal lies in our cooperation. Despite geopolitical rivalries, the astronomical community has worked across nations to observe and model this interstellar visitor. Here, at least, humanity behaves like a species capable of uniting under the banner of curiosity. At the same time, Our limitations are plain: ambiguous gas detections, uncertain size estimates, incomplete characterizations. An advanced civilization could measure our progress by the gap between our aspirations and our actual capabilities. Ultimately, the most telling measure may be how we handle ambiguity. Science thrives on patience and caution, but public discourse thrives on certainty and spectacle. 3. Atlas thrusts us into the tension between the two. Can we remain disciplined in the face of mystery? Can we resist the seduction of premature conclusions while still nurturing imagination? These are not trivial questions. They may be the very qualities that determine whether a civilization is ready to engage with others. Even if 3I Atlas is nothing more than a frozen fragment from another star, it functions as a mirror, reflecting humanity's intellectual adolescence. Whether designed as a probe or not, it tests our institutions, our media, our science, and our imagination. Each interstellar visitor thus becomes a rite of passage, a cosmic examination of our readiness for the broader stage. And so the comet continues toward perihelion, carrying with it not just dust and ice, but the questions it plants in our minds. In the end, the test may not be about what we learn of 3I Atlas, but about what 3I Atlas reveals of us. Part 13. The limits of what we know: data, gaps, and next steps. Science is always a dialogue, a conversation between the neat models we sketch in theory and the unruly signals the universe sends back when we try to measure them. With 3I Atlas, that dialogue has been at once illuminating, maddening, and full of contradictions. It is a case study in how knowledge grows, islands of certainty rising from oceans of doubt, stitched together by fragile bridges of inference. Let's begin with the firm ground. Astrometry, the art of pinning an object's position against the backdrop of stars, provides the bedrock of our understanding. Multiple observatories across the world have now tracked 3I Atlas for months, stitching together a long arc of data points that lock in its path with remarkable precision. These measurements confirm what first triggered excitement: an eccentricity of about 6.1, far greater than unity, marking a hyperbolic orbit that guarantees it is not bound to our Sunday. Its inclination 175 degrees confirms a retrograde passage, sliding almost perfectly against the grain of planetary traffic. The sequence of encounters with Mars, Venus, Earth, and Jupiter, though distant, are mapped with the accuracy orbital mechanics allows. That much is not up for debate. Hubble's eye adds another solid pillar. Its images show a coma already well developed, with a hazy shroud of gas and dust enveloping the nucleus. The data reveal a faint antisolar tail too, the classic hallmark of an active comet driven by sublimating ice. Surface brightness modeling constrains the nucleus radius to less than 2.8 kilometers, perhaps much smaller, and estimates of dust production rates fall between 10 and 120 kilograms per second, comfortably within ranges measured for solar system comets at comparable distances. Photometric campaigns worldwide have watched the object brighten steadily as it drifts sunward, its light curve tracing a trajectory that, while not perfectly canonical, broadly mirrors the behavior of natural comets. Even preliminary color data suggest its dust properties are not wildly alien. Variations exist, but nothing yet screams unprecedented chemistry. Yet these islands of certainty are surrounded by gulfs of ignorance, chief among them composition. Spectroscopy, the gold standard for deciphering what comets are made of, has thus far come up empty. Teams scanning for water vapor, carbon dioxide, carbon monoxide, cyanide, and other telltale gases have detected nothing definitive. Instead of bright emission lines, they've found only upper limits, constraints on how much of these species could be hiding below detection thresholds. This silence could mean several things. The volatiles are indeed present, but at low levels. They are dominated by exotic compounds not easily observable, or the observations themselves, hampered by faintness and distance, simply lack the sensitivity required. The precedent of 2-1 Borisov tempers our impatience. Its most revealing spectral fingerprints only emerged near perihelion, when solar heat pumped activity to levels detectable from Earth. 3. I-Atlas may yet speak chemically, but for now, it whispers too softly to hear. Morphology, too, remains a puzzle. Hubble's sharp vision separates nucleus from coma better than any ground-based facility, yet models of the underlying body must still assume values for dust grain size, composition, and scattering efficiency. Each assumption introduces systematic uncertainties, so every estimate of size, albedo, or activity is wrapped in wide error bars. We still do not know its rotation period. Most comets betray themselves with periodic brightness variations as active patches sweep in and out of sunlight. 3 I-Atlas has shown no such rhythm, perhaps because it rotates very slowly, or is shaped nearly spherical, or presents a pole-on view. Each explanation is plausible, none is confirmed. Without this knowledge, predicting how its appearance will evolve as it nears the Sun remains guesswork. Solar conjunction adds to both the frustration and the opportunity. As the comet rounds perihelion in late October 2025, it will disappear behind the Sun from Earth's vantage. Ground-based telescopes will be blinded by glare, just as heating should peak and unusual activity might blossom. Hubble can probe closer to the Sun than most instruments, but it too has safety limits. Solar observatories might attempt the task, but teasing a faint, moving smudge from the brilliance of our star is a Herculean challenge. The comet's post-conjunction reappearance in December will be crucial. Many comets emerge transformed, their structures cracked, their activity re-energized, their volatile reservoirs laid bare. 3 I-Atlas might reveal then what it hides now, but even those observations will remain bounded by our tools' limitations. Earth's atmosphere blurs ground-based imaging and filters out spectral lines. Space-based assets are few, oversubscribed, and restricted in wavelength. No single observatory can capture all the necessary data. What emerges will be a mosaic, pieced together from disparate instruments and stitched across time. That mosaic will inevitably contain gaps. These gaps are fertile ground for interpretation. When the error bars are wide, many models can fit the same data. Conventional comet physics works reasonably well, but leaves anomalies at the margins. Exotic hypotheses, artificial origins, engineered trajectories remain compatible too, precisely because our constraints are still so weak. Until more data arrive, neither camp can close the case. Institutional responses reflect this tension. NASA and ESA emphasize the clear cometary evidence, preferring to foreground what is known. They acknowledge uncertainties but frame them as questions for further study, rather than mysteries hinting at the extraordinary. This approach maintains scientific credibility and public reassurance, but it risks downplaying just how little we actually know. Astronomers walk the same tightrope, carefully hedged statements consistent with, not inconsistent with, plausibly explained by, reflect honest caution, but frustrate a public hungry for definitive answers. Meanwhile, peer review churns slowly. Early discovery notes and preliminary analyses circulate on preprint servers, where speculation can run ahead of verification. The most decisive papers will only appear months from now. Once perihelion has passed, data have been analyzed, and the community has weighed in. This is science at its most deliberate, good for accuracy, less good for satisfying curiosity in real time. Thus, 3 I-Atlas remains a paradox, an object both well characterized and deeply mysterious. We know its orbit with exquisite precision. We know it is active, small, and dusty, but we do not yet know its chemistry, its spin, or its structural heart. We cannot say whether its anomalies are trivial quirks of dust, physics, or hints of something unprecedented. The next steps are clear: spectroscopic campaigns as it brightens, coordinated post-conjunction monitoring, detailed modeling of its coma and tail, and above all, patience. Only time and observation will close the gaps. For now, the comet inhabits the liminal space between knowledge and ignorance, the very space where science and wonder thrive. Competing research groups often arrive at divergent conclusions, even when working from the same observational data. The disagreements are rarely about competence. They arise from the assumptions built into models, the statistical tools applied, and the weight assigned to different pieces of evidence. One team may emphasize photometric trends, another spectroscopic non-detections, while a third highlights orbital geometry. These debates ripple through conference halls, light up preprint servers, and slowly distill into peer-reviewed literature, though the process often stretches across months or even years. The difficulty is magnified by context. With only 3 confirmed interstellar visitors, Oumuamua, Borisov, and now 3, I-Atlas, we lack a baseline. There is no catalogue robust enough to tell us what normal looks like for such wanderers. What seems anomalous in 3I Atlas today may appear routine once we have dozens of examples to compare. This is where the Vera Rubin Observatory looms large. Equipped with its 8.4-meter mirror and staggering 2 gigapixel camera, Rubin will scan the entire visible sky every few nights. Conservative models suggest it could spot anywhere between 6 and 50 interstellar objects annually, depending on their size and activity. Such a deluge will transform our field. The Rubin era should provide the statistical muscle to address questions that now hang unresolved. Are alignments with the ecliptic genuinely improbable, or simply artifacts of how our surveys are tuned? Do strange brightness morphologies represent exotic physics, or just natural dust scattering under conditions we've rarely witnessed? How common is the specific blend of traits? 3I Atlas exhibits its retrograde orbit, faint but persistent activity, ambiguous chemistry. With larger numbers, patterns will emerge, but new opportunities will bring new burdens. A rapid discovery rate will overwhelm the painstaking, bespoke methods we've used so far. We won't be able to lavish months of global follow-up on every curious dot of light. Automated classification pipelines will become essential, yet these systems must be trained on a tiny, skewed sample. Early choices about which candidates merit intensive study could bias the very population statistics we seek to establish. International collaboration will become even more critical. The current system, where researchers manually coordinate observations across facilities, won't scale to dozens of new objects each year. We'll need faster protocols for dividing, observing time, sharing data, scheduling spectroscopy, and distributing results quickly enough to guide subsequent observations before the objects vanish back into interstellar night. The story of 3I Atlas has already shown both our strengths and our limits. We've proven that the global astronomical community can rally with astonishing speed, mounting coordinated campaigns under the glare of public attention. But we've also discovered gaps in spectroscopic sensitivity, in our ability to disentangle coma from nucleus, in the precision of our models when observations are sparse. Perhaps the most valuable lesson has been cultural rather than technical. 3I Atlas has forced us to practice managing uncertainty in real time, explaining what we know, what we don't, and what we might. Drawing the line between healthy speculation and unfounded hype is not easy, but it is a skill we'll need as such discoveries multiply. Our present ignorance stems partly from the inherent challenge of the task. These objects are small, faint, fast, and fleeting. We catch them only briefly, armed with finite instruments under imperfect conditions. And yet the very fact that we can wring coherent science from such elusive visitors speaks to extraordinary progress in our theoretical frameworks and observational tools. As 3I Atlas rounds perihelion and drifts outward again into the dark, new data will refine our estimates of its size, spin, and chemistry. But each answer will open new mysteries, each solved puzzle revealing subtler complexities in the physics of interstellar debris. Science thrives in this space between what we think we know and what the cosmos chooses to show us. On that stage, 3I Atlas has proven a gifted conversationalist, teaching us not only about itself but about how we, as a species, learn from fleeting encounters with the unknown. Part 14. If chosen, by whom and why we return. The solar system spins like an ancient record, its planets and dust following grooves cut long before humanity learned to listen. Into this music dropped 3I Atlas, the cosmic needle that traced our disk with uncanny precision before preparing to lift away into silence once again. Its passage has been equal parts physics, experiment, and symphony, a performance that leaves us haunted by a single question: was this music composed, or are we only hearing melody in the static of chance? The case against intention rests on firm ground. Every measurable feature of 3I Atlas fits comfortably within the playbook of natural celestial dynamics. Its hyperbolic orbit, with eccentricity near 6.1, is exactly what one expects of an object that has fallen into and out of the sun's gravitational grip. Its velocity relative to the local standard of rest mirrors the motions of thick disk stars, hardly exotic by galactic standards. The apparently purposeful ecliptic alignment, when examined with sober eyes, resolves into a product of selection bias and gravitational focusing. The planetary flybys look like a choreographed tour only until you measure the distances tens of millions of miles, far too wide for reconnaissance or slingshot maneuvers. And most convincing of all, Hubble's eye sees the telltale haze of a comet, sunward jets of dust, a faint tail dragged away by radiation pressure, dust production rates measured in kilograms per second, entirely ordinary for a nucleus a few kilometers across. No unexplained accelerations, no strange energy signatures, no structured emissions, only ice turning to vapor under the sun, as physics has ordained for billions of years. The apparent oddities melt under scrutiny. Forward scattering explains the asymmetric brightness. Nucleus size estimates shrank once coma contamination was corrected. Ambiguous spectroscopy reflects the difficulty of detecting faint gas lines, not necessarily their absence. By this accounting, 3I Atlas is a comet, nothing more. And yet, the nagging remains. The immaculate ecliptic threading, the awkwardly convenient solar conjunction, the asymmetry of brightness that never quite resolves, the silence in spectroscopy where whispers of water and carbon dioxide ought to be. Each anomaly alone has a conventional answer, but together they form a pattern that resists easy dismissal. The unease is not in the data points themselves, but in the way they accumulate, like brushstrokes that hint at a figure hiding within abstraction. If 3I Atlas were artificial, it would be a masterpiece of camouflage. Too obvious a machine, and it might provoke fear, even hostility. Too ordinary, and it would teach us nothing about our ability to detect the extraordinary. Instead, it sits in the middle, balanced on ambiguity, suspicious enough to spark debate, natural enough to avoid panic. A perfect test case, if testing is the point. Surveillance seems unlikely. The distances are simply too great. No probe would settle for a 270 million kilometer close approach to Earth if reconnaissance were its mission. The geometry often hides planetary surfaces rather than revealing them. A true observer would fly closer, deploy subprobes, linger in orbit. By those standards, 3I Atlas looks almost deliberately inefficient, which raises another possibility. Perhaps the mission is not to observe planets, but to observe us. In that light, its success is undeniable. Within hours of discovery, telescopes worldwide coordinated to follow its path. Astronomers published preprints, debated data, argued interpretations. Agencies like NASA and ESA issued cautious statements. Media outlets flooded the public sphere with headlines veering from sober science to speculative fantasy. Social media split into factions, skeptics, enthusiasts, conspiracy theorists. Every flaw in our instruments, every strength in our collaboration, every bias in our interpretation has been laid bare. If this were a test, the examiners would already have thick dossiers on humanity's scientific maturity and cultural psychology. The timing could hardly be better. We are at a hinge point in history, our telescopes powerful enough to detect and study interstellar visitors, but not yet sharp enough to reveal every detail. We can measure orbits to fractions of an arc-second, but our spectrographs strain to pull faint signals from noise. We can mobilize global campaigns of observation, but our interpretations wobble between conservatism and speculation. If an advanced intelligence wished to probe our readiness for greater contact, they could hardly have chosen a more revealing scenario. The question of by whom sends us spiraling into speculation. A civilization capable of setting such a trajectory would wield technologies beyond our imagining, propulsion systems that render light years trivial, computational capacities that chart gravity's tug across centuries with pinpoint accuracy. Their motivations may be equally opaque. We project our own survey missions, reconnaissance, catalogues of habitable worlds, but their goals may be as incomprehensible to us as particle physics would be to a medieval farmer. We may be asking the wrong questions, looking for familiar intent where none exists, or where intent takes a form alien to our categories of thought. And yet there is something almost elegant in the idea that 3I Atlas is less about what it is than about what it makes us reveal. Our debates, our measurements, our news cycles, our imaginations, all of it paints a portrait of a young civilization grappling with the idea of not being alone. Whether or not anyone beyond us is watching, we are, in a sense, watching ourselves. Even if 3I Atlas proves to be nothing more than a lump of frozen debris, it has already succeeded as a mirror. It has shown us our capacity for global cooperation, our hunger for meaning, our struggle to balance skepticism with wonder. It has tested how we manage ambiguity, how we communicate uncertainty, how we resist or succumb to our biases. These are lessons as profound as any data on volatile ratios or dust production rates. The needle has traced its groove. Soon it will lift, vanish into interstellar night, and we will be left with records and reflections. Did we hear music, or just the scratch of physics on vinyl? Perhaps the distinction is less important than the fact that we listened at all. If the trajectory was chosen, then somewhere beyond the stars, unfathomable minds are noting how well we attended their score. If it was not chosen, then we composed our own music woven from mathematics, observation, and curiosity. Either way, the song reveals what kind of species we are becoming, standing at the threshold of cosmic awareness. In the end, perhaps this is the real choice. Not whether 3I Atlas was guided, but whether we are willing to be guided by the questions it forces us to ask. Mysteries matter less for the answers they provide than for the transformations they spark in those who seek them. On that measure, 3. Atlas has already succeeded. It has given us a glimpse of ourselves as listeners in a cosmic symphony, players on a stage we are only beginning to recognize. Whether chance or intention, it leaves us with the same gift, the reminder that to wonder is itself a form of music, and to search is already to belong.